Here's GeoGebra. I drew a triangle. Let's name it something. What do you want to name it?
GeoGebra.
What's the name of this triangle?
Jacob.
Okay. We need 3 names, so we need like a first, middle, and last name. What's the middle name?
Jones.
Juan.
Wait, all J's. Come on, all J's.
What's the last name?
Khalil.
Khalil?
Yes.
How do I spell it?
K-H-A-L.
Nelly, how do I spell it? You seem to know.
K-H-A-L-I-L.
And we're live! Shout out to Juan Khalil. Does he go by Jacob too?
Juan Jacob Khalil.
Yeah, boy. All right. Does he have a middle name?
It's Jacob Juan.
Juan Jacob Khalil.
No, I think it's
Nelly, what's his middle name?
I don't know.
All right, well, get on that. Metaphorically.
I'm gonna make this my next.
All right, so here's the triangle. Now check it out. I can drag this triangle all over and make different triangles. Like this is an acute triangle. This is a right triangle. I can also make an obtuse triangle. Right? You cool with that? Wow, amazing. Let's go back to the one we had on that guy. Something like this. Right? Okay, cool. Let's make medians first. Median is what to what? What do we connect when we make a median?
Two shared side.
Vertex to midpoint. We have vertices. Now we need to find a midpoint. I'm going to use the midpoint tool. Boop. And all I have to do is connect. I'll go Jacob Khalil, and then I put a point in between. That's the midpoint. If I drag, still the midpoint, right? All right, ladies in the back, you good?
That's Jacob and Khalil's child.
Juan and Khalil, there's their midpoint. There's Jacob and Juan's midpoint.
What kind of weird love triangle is
That's
this?
a love triangle, if you will. Yeah. All right.
Juan and Jacob.
Are we good? Are we good? Are we good? All right, so those are all midpoints of the triangle.
Khalil had a child.
And remember, medians are vertex to midpoint, right? So I use my segment tool, vertex to midpoint. I don't want to go midpoint to midpoint because that's a mid-segment, right? I want medians. So here are my medians. 2 lines intersecting at a point. Should we be shocked?
Yeah.
No, 2 lines hitting at the same point? It's going to happen unless they're parallel, right? Should not be shocked. But what about 3 lines? Oh, yeah. They all intersect at a point. I'll call it D.
Aw, man.
So, that's the triangle we had on our thing, right? What if I change the triangle? Will they still be concurrent? Yes. No matter what triangle I make, they're always concurrent. Not only are they concurrent, but D, the center that we made, it's always inside the triangle, right? That's interesting.
Juan still like a sexy motherfucker.
Hey. So, let's go back to here. What? Yeah, you don't need to ask permission. All right. Medians. G. That point right there is the intersection of the medians, and they will always intersect at one point. They're always concurrent, no matter what the triangle. And we call this, if you're in Eastern Europe, you call it a medicenter, so mark. Medicenter. That's what you call it in Eastern Europe.
Sounds like a hospital.
Which makes sense, median medicenter. That's the one I learned. I don't know why, I've never been to Eastern Europe. But the way we say it in America and everywhere else is called the centroid.
That sounds.
Okay? Now, what is special about the centroid? Well, here's what's special about the centroid. It's the center of mass. So it turns out, if you wanted to find the balance point on this triangle, that's the point. That's where you put your finger. Now, if the centroid is the center of mass, and it is, should we be shocked that it's always inside the triangle? No. Here's a ruler. Where do you think its center of mass is?
6 inches.
Probably in the middle, right? Somewhere around there, right? Well, what if the ruler were heavier on one side? Like heavier on this side? Where would the center of mass be? More towards that side to balance out, right? If it's really heavy, it would be like here. will it ever be on the outside? The center of mass. No, right? The balance point would never be on the outside. So the centroid is the center of mass. No duh is always in the middle of the triangle, right? Somewhere inside. Never be on the outside or on it, right? No matter how we stretch it, it's always going to be somewhere inside the triangle. Just like no matter where I put weight on this teeter-totter, the balance point's going to be somewhere on it, right? It's not going to be over here. How are you going to balance that, right? So when I ask you for an acute triangle, it's on the inside. For a right triangle, it's on the inside. Where on the inside, I don't know. Depends on how we stretch it, right? Could be like really far over to the side or in the middle, right? It depends on how the triangle's constructed. Or for an obtuse triangle, right? It's all on the inside. And that should not surprise us because the centroid is the center of mass, right? It's always going to be on the inside. You cool with that? Now, how do we find the centroid? Well, we find the medians, the midpoint, right? We connect it to the vertex, and where they intersect will be the center of mass, the centroid, or the medicenter if you're Mark, right? Mark, you weren't listening, but the medicenter is what they call it in Eastern Europe.
No, yeah, I heard.
Got it, okay. That's the one I like the best, but I'll accept either.
Bro, Centroid sounds like it's a Terminator.
It does, doesn't it?
Medicenter sounds like it's a...
Now, there are more properties that we'll talk about. We're not going to talk about them right now. We have talked about it before, though. We did a proof similar to this. Turns out that this will always be twice as big as this. Always. We did a proof last week about that. Cool. Let's look at number 1. Angle bisectors. Will the angle bisectors always be concurrent? Let's find out. All right, I have to delete this stuff. Not the good stuff.
Yeah.
All right, so angle bisectors. Angle bisectors is a triangle, right? So I'm going to take my angle bisector tool, and I'm going to go Juan, Jacob, Khalil. And that line right there cuts this angle in half. Where does it hit the opposite side? I don't know. Random point. Let me show you. See, it doesn't always cut the other side in half. Right? Sometimes it's not cut in half. But it always cuts this angle in half. You cool with that? That's angle bisector. If I make 2, Jacob, 1, Khalil, notice they intersect. That should not surprise us. 2 lines intersecting, boring. Right? All 3, that would be surprising. Now, this triangle is very similar to the one we have on our page. So yeah, they all intersect at a point. But will they be concurrent if they're a right triangle? Yeah. What about an obtuse triangle? Yes, still concurrent, right? And not only are they always concurrent, but where is A always located? Inside. So the angle bisectors are always concurrent at point G. We call point G the in-center. And when it's acute, 90, or obtuse, right? It's inside. In center. I-N, center. Yep.
Wait, so how do you, so like
Guys, quiet, I can't hear Mark. Sadie, can't hear him.
there's like centroid and incenter, like how do you know which one to use?
Well, the in-center is the intersection of the angle bisectors, right? And the centroid is the intersection of the medians, right?
Are they just like different names for like each like?
The intersection of the medians is called the centroid. The intersection of the angle bisector is called the in-center. They have different properties. Like the centroid is the center of mass. The in-center's property is this. And I'll show you it better on GeoGebra because it's hard for me to do it on here. It turns out that G, actually let's do this. It turns out that G, point G, is the same distance to every side of the triangle. And we measure distance, we always measure 90.
right? Straight up, like my distance, my head to the ceiling, I go straight up. I wouldn't measure it like that. I would not measure the distance from my head to the ceiling at an angle, would I? I go straight up at 90. So from here to here, my head, the ceiling, up to 90, right? Same thing over here. What do you think is special about G? It's the same distance to every side. What does that tell you?
It's like right in the center.
Center of what?
The triangle.
Kind of. There are lots of
Center of
centers.
mass.
Nope. Center of mass is centroid.
Damn.
You want to see something cool? Right before you go, here we go. Sit down. I need to draw a perpendicular so I can measure the distance, right? I'm going to measure the distance from A to the outside. Oh, I'll see you next time.
Mac, it's weird because I actually understand this.
Well, it's very basic stuff right now. So make sure you do. That way we can get the hard stuff.